So good afternoon, everyone. So today we'll be presenting on the topic of proton exchange membrane, or PEM for short, fuel cell efficiency, based on the uh, research paper by Benny Asmidoimin. So this study basically evaluates how hydrogen and oxygen availability impact PEM fuel cell efficiency. So I am Senapati JD with the registration number 4200, and so I will be giving you the introduction and the literature summary of this paper, and then I'll pass on the presentation to my team members here, and then let me get started without further ado. So about the paper, like I said before, the authors of this paper mainly is this research paper is basically mainly by Benny Doimin. So Asmi Maud Zamlan and Rani Manuel and Clara Valdez was also part of this conference paper, and this paper was presented in the International Tibet Academic and Research Symposium on May 2025. So without further ado, let me give you a basic introduction and a literature review summary of this paper. So let me tell you what PEM fuel cells are. So PEM fuel cells, basically they convert chemical energy from hydrogen into electrical energy through a electrochemical process. So in this process, one of the main advantages of PEM fuel cells is that the only byproduct that is released to the environment is water in the form of water vapor. So any harmful gases are not, like greenhouse gases, are not released to the environment. So this is related to green energy. So in our world, since we are taking more and more steps towards green energy, a key technology in the shift uh, towards clean, sustainable energy is this PEM fuel cells. So let me continue. So what are the importance of green energy? So as I said before, since there's a high demand for green energy, the main reason for that is the climate change that is happening in our world right now. And so since most of the fuels are uh, energy is produced using fuel cells, we have to change this into a more sustainable green energy method. So what are the roles the fuel cells play in green energy? So PEM fuel cells provide a clean and efficient alternative. And this is also very efficient and used in many uh, applications like transportation, backup power, and also, like I said before, the main advantage is that this only emits water vapor as a byproduct to the environment. So, like I said before, why do we use PEM forces? The main reasons are high efficiency. They have a high energy conversion efficiency compared to other fuel cells, and the low emissions, which is only water is released to the environment as a byproduct, and also the versatility, which means that it is used in a wide range of applications such as vehicles, backup power systems, and also even space explorations. So real world applications for PEM forces are transportation, like I said before, space exploration, and also backup power systems. Okay, so what are the objectives of the study done by Benny Asmi-Doimi? So mainly the primary goal of this study was to analyze how the efficiency uh, of the PEM fuel cell affected by hydrogen and oxygen under different load conditions. So by understanding this behavior, we are able to predict or find a way to optimize the efficiency of the uh, fuel cell and the performance this fuel cell is used in real world applications. So let me give a small summary of the literature review in the conference paper. So theoretically, PEM fuel cells should deliver 1.23 volts, but due to losses, the practical values are ranging from 0.4 to 0.9 volts. And most of these losses are actuation losses, ohmic, and diffusion losses. So these losses affects the efficiency. So that's the main reason of this conference paper. How uh, due to these losses, how the efficiency of the PEM fuel cell is managed by hydrogen and oxygen in the different load conditions. So that's it from my end. I'm gonna pass on this presentation to my teammates. Thank you.
Methodology and experimental setup. Let's start with the experimental setup. The setup includes a hydrogen generator, storage canisters filled with distilled water, a PEM fuel cell, and an energy control board that is connected to a computer. The generator produces hydrogen through electrolysis. The fuel cell then converts this hydrogen into electrical energy. The control board and software allow us to simulate different load conditions by varying the current and track how the fuel cell responds. This setup helps us to measure efficiency under real world operating scenarios. Let's move to the next slide. Safety measures. Safety is critical when dealing with hydrogen and fuel cells. To protect the membrane of the fuel cell, it must always be dry. So water is only added to the storage canisters and not to the fuel cell. We also maintain the water level below 5 cubic centimeters to avoid overfilling. Another key point is that the hydrogen generator is never operated above 2.3 volts. And importantly, the fuel cell and hydrogen generator are never connected at the same time to avoid short circuit and damaging both components. These steps ensure safe and controlled operation. Let's move to the next slide. Now, let's look at how hydrogen is produced. We begin by adding distilled water to the storage canisters. Then, we seal the hydrogen outlet to allow pressure build inside. Then, we activate the hydrogen generator and set the current to 650 milliamps to generate about 15 cubic centimeters of hydrogen gas through the electrolysis. Once the required amount of hydrogen is produced, we stop the electrolysis by setting the current to zero. Before using the fuel cell, we perform a quick purging by removing any residual gases. If needed, we can repeat this process to generate more hydrogen. It is a simple process to produce hydrogen on demand. Let's move to the next slide. Once hydrogen is ready, we move on to the operating of the fuel cell. The fuel cell is connected to the energy control board and we switch to the fuel cell mode. We set a target current, usually between 200 and 400 milliamps, and then record the fuel cell's output, voltage, current, and duration. A healthy fuel cell under optimal conditions should output around 5000 millivolts. If the voltage is around 3000 millivolts, it suggests that the cell might be aged or underperforming. By observing these benchmarks, we can assess the condition and efficiency of the fuel cell over time. We'll move to the next step. Finally, we can calculate the fuel cell's efficiency using this formula. In the formula, UI means average voltage, II means average current, Ti is time, VH2 is the hydrogen volume, and HU is the hydrogen heating value. This equation tells us how efficiently the fuel cell converts the chemical energy of hydrogen into electrical energy. This formula is crucial for designing real-world fuel cell systems where every percentage of energy matters.
I'm Soisa WSN, registration number EG 2020-4321. I'll be presenting the results analysis section of this research review. So let's begin with the data table from the experiment that we have extracted from the research paper. So this shows the PEM fuel cell consumption experimental data collected by the authors in their study and how we have used this study for our own project. So the table includes hydrogen consumption, operating duration, voltage, and current recorded at 6 points. As expected in PEM fuel cells, hydrogen consumption increases over time. from 0 to 25 cubic centimeters. And alongside this, voltage drops slightly from 2990 millivolts to 2.87 volt, and current decreases from 0.354 to 0.337 amperes, as you can see in the table. So these changes are the typical in fuel cells under continuous load and reflect natural energy losses such as heat or increasing internal resistance. So the researchers used a standard formula within this research to calculate fuel cell efficiency, which compares the electrical energy output to the energy content of the consumed hydrogen across different measurements. So the efficiency consistently ranged between 0.442 and 0.444, or about 44% percentage. And this shows that the system maintained stable operation throughout the test despite gradual performance drops in voltage and current. Here, in this research, the authors plotted a graph showing hydrogen consumption and energy efficiency over time. As seen, hydrogen usage rises steadily with time, while efficiency remains flat close to 44%. So this implies the fuel cell managed a steady energy conversion rate, which is an indicator of reliability in controlled lab conditions. So we have taken this value and also this research to our project as well, because this has emphasized the reliability in controlled lab conditions. So such a consistent output is promising for practical applications, as we are doing in our project as well, especially in systems requiring short bursts of clean energy. So finally, the authors in this research discussed how the different measured parameters are interconnected. As more hydrogen is consumed over time, the fuel cell experiences a slight drop in voltage and current. Due to increased resistance and other physical limitations inside the cell, even though these changes occur, the fuel cell's efficiency remains largely unaffected, which indicates good system design and operation. So from this, we understood that while PEM fuel cells do lose some performance over time, they still provide consistent energy conversion, making them suitable for stable green energy applications. So that wraps up the analysis of the results from this study. So next, Sandali will take you through what these findings mean and possible future directions highlighted in the research. Thank you.
Now let's look into the discussion, conclusion, and future work. Hydrogen generators use electricity to split water into hydrogen and oxygen, and fuel cells recombine those gases to generate electricity and water. So, in this study, we observed an average energy efficiency of approximately 44%, as shown in this chart. This number, while not perfect, it is quite impressive for a PEM fuel cell. It reflects consistent operation with relatively low performance degradation. The losses in efficiency mainly from unavoidable factors like heat generation, internal electrical resistance, and imperfection in catalysis. It's important to note that this level of efficiency aligns well with what is considered standard in practical applications, especially where stable and predictable power output is more critical than maximum efficiency. Now let's move into the next slide. This is the performance discussion of this system. As the experiment progressed, it showed a slight voltage drop from 2990 mV to 2870 mV and a current decrease from 356 mA to 334 mA. While this drop appears small, it indicates internal resistance effects and gradual catalyst age. Interestingly, the hydrogen consumption increased linearly over time, showing that the fuel consistently generated electricity as long as fuel was supplied. The stable current and voltage profiles over time confirm the reliability of this setup for short duration energy applications. This is this is especially relevant in backup power systems, portable electronics, and even drone or satellite power module applications where short bursts of stable power are more valuable than long-term operation. Now let's move into the next slide. To summarize, the investigation confirmed that PEM fuel cell efficiency is tightly linked to load demand and availability of hydrogen. It also showed that injecting pure oxygen into the system leads to a noticeable voltage boost, improving the power output. These findings are consistent with existing research, confirming that fuel cell performance can be improved through controlled gas input and monitoring load behavior. Overall, this system demonstrated efficient and reliable performance under different operating scenarios, making it suitable candidate for both education setups and prototype development environments. Let's move into the future research. Moving forward, several research directions can build on these findings. First, we could explore how pressure and temperature fluctuations affect performance. In real world, fuel cell applications, especially in vehicles or aircrafts that face dynamic environments, understanding these impacts are crucial. Second, improving catalyst materials could enhance reaction rates and reduce hydrogen consumption. This is particularly important for making fuel cells more cost effective and environmentally sustainable. Third, long-term duration tests are essential. While short-term performance is stable, it is vital to investigate how electrode materials degrade over time. And finally, it is possible to explore integration into aerospace and transport technologies, where PEM fuel cells could replace or supplement traditional combustion engines in lightweight and efficient ways. So we have come to the end of our presentation. Thank you.